When you're asked to find the domain of a function like this one, it can feel like you have to spend forever trying to figure out what does work. But the truth is that you don't need to check for every number that does work. Instead, you only need to catch the very few that don't. And as it turns out, there's only one technique and 3 red flags that we have to look out for. If you master these, you'll be able to solve almost any domain and range problem you see. Now, the first problem we face with domain and range is sometimes just understanding what they even are. And I like to think of a vending machine analogy. The domain is the set of buttons that we're allowed to push. Those are the keys on the outside of the vending machine that we can press. And as a result of pushing those buttons, the range is the set of all the snacks that can possibly come out of that vending machine. The machine itself is our function. Every vending machine is a little different in the same way that every function is a little different. We're going to have different buttons on the outside that result in different snacks coming out of the machine. So as an example, think about the vending machine or the function given by x plus 1. The buttons on the outside of the machine are all the x values we can input. So for example, we could put in -1 or press the -1 button, and then the machine takes that -1 input and says that the output is -1 plus 1 or 0. So the snack coming out of the vending machine, the output is 0. -1 goes in, this particular machine, this particular function spits out 0. Or we could put in 0 itself, and an input of 0 into this function gives an output of 1. So we were able to put in at least one negative value. We were able to put in 0. We're also able to press the button 1 or put in the input 1, and this function gives out an output of 2. And it's not just integers. Think about plugging in fractions. Putting 1/3 into this machine gives an output of 4/3, or square roots. Putting in the square root of 5 gives an output of 1 plus root 5. So all these x values, -1, 0, 1, 1/3, root 5, are all examples of values that exist in the domain of this function f. And all of these values in purple here, 0, 1, 2, 4/3, 1 plus root 5, these are all examples of values that are in the range of this function f. They're outputs of the function. We run into a problem though, because we just looked at this input-output idea when we had the function's equation. We had the equation of the function. But what do we do if we only have the graph of a function? Well, when we only have the graph of a function, we can use what we call the flashlight trick. And the idea is that we want to shine a flashlight from every direction, the top, the bottom, the left, and the right, onto the function and see where it casts a shadow. So if we imagine a flashlight shining above the function, or shining from the top here, and we imagine moving this flashlight back and forth to the left and right above the graph, we can see that the shadow it would cast on the x-axis is this portion right here. And if we were to shine a flashlight from the bottom, this left side of the line would cast a shadow on the x-axis over here on the left. Whatever shadows we get along the x-axis when we use a flashlight above the graph and below the graph make up the function's domain. So because that shadow would extend infinitely to the left and infinitely to the right, and there would be no points at which a shadow would not be cast, the domain of the function is all real numbers, or the entire real number line, all values of x. And we can write that this way as -infinity all the way to positive infinity. On the other hand, the range is what we get when we shine a light from both the left and right sides. So if we shine a light from the right side of the graph, then this upper portion of the graph casts a shadow along the y-axis that's above x equals 0 here. And if we shine a light from the left, this lower portion of the graph is going to cast a shadow on the y-axis that's below y equals 0, below the x-axis. So because flashlights on the left and right would illuminate the entire y-axis, that means the range is also -infinity to positive infinity. It's the entire y-axis. And seeing this kind of domain and range brings up an important point, which is that we use a parenthesis when a value is not included in the domain or the range, and we use a bracket when it is included. When we have -infinity and positive infinity, we always use a parenthesis because those values aren't real numbers. They're just representations of this idea of infinity. So using this flashlight trick, let's look at the graph of a parabola. If we shine a flashlight above the graph up here up top and below the graph down here at the bottom, we can see that this right side of the graph, everything to the right of the y-axis, using a flashlight above the graph, would cast a shadow along the x-axis here. And if we shine that light above the left side of the graph, everything to the left of the y-axis, this left side would cast a shadow along the x-axis here. And we can see that that shadow would extend infinitely in both directions as the parabola widens out to the left and right, which means that the domain of this function is again negative infinity to positive infinity, all real numbers. On the other hand, though, if we look at the range, if we were to use a flashlight from the right side of the graph and we move the flashlight up and down over here on the right side, we can see that the parabola is going to cast a shadow along the y-axis here. And the same is going to be true if we have the flashlight shining from the left. This left side of the parabola is also going to cast a shadow here. Notice that there's no shadow cast below the x-axis, only above it, which means that the range is defined only from 0 to positive infinity along the y-axis. And so we say the range is 0 to positive infinity. And here, using interval notation, this is called interval notation, we see our first square bracket because 0 is a real number of finite value, and we want to specifically say that 0 is included in the range, while we continue to use parentheses with infinite values, both negative infinity and positive infinity. Let's look at one more to make sure we understand the flashlight trick here. We have a semicircle, and we can label some of the points along the circle. We can see that this point at the left edge is at -4, 0. We have this point at 0, 4, the highest point of the semicircle, and this point at 4, 0, the rightmost point. So if we use our flashlight trick and we shine a flashlight above the semicircle, we can see that it casts a shadow from -4 to +4 along the x-axis. So the domain is -4 to +4 with both of those values included. So we have square brackets attached to each side of the domain's interval here. On the other hand, if we use a flashlight along the left side or the right side of the semicircle, we can see that it's going to cast a shadow along the y-axis here from 0 to 4, which means the range is 0 to 4 with both of those values included, and we again use brackets. And it's helpful here too to understand domain and range to see what happens if we were to, for example, shift this semicircle 1 unit to the right. In other words, a perfectly horizontal shift. Well, as we can see, the range is the same because the y values for which this semicircle is defined remain the same. The range is still 0 to 4. But the domain, because of the horizontal shift, moves from -4 to 4 to 1 unit to the right, -3 to 5. In the same way, a perfectly vertical shift would leave the domain unchanged, but would shift the range. Okay, so we understand how to read the domain and the range from a graph, which is great when we have the graph, but we're not always going to have a picture of the function. Sometimes all we have is the function itself. And when that's the case, we have to look for 3 red flags. The first is that we can't divide by 0. So if we have a function like this one, 5 over x minus 3, we know that x cannot be equal to 3 because the value 3 would make the denominator 0. We'd have 3 minus 3, we'd get 0 in the denominator. That would make the function undefined, which means x equals 3 cannot be in the domain, so we exclude it. The reason for that is because, and this is a graph of 5 over x minus 3, any value that makes the denominator 0 is a vertical asymptote in the function. And again, using our flashlight trick, we can see that this left piece of the function would cast a shadow along the x-axis all the way here, but not right at x equals 3 itself. This right side piece of the function would cast a shadow for this entire part of the x-axis, but not right at x equals 3 itself. So the entire real number line, the entire x-axis, would be included in the domain, except right at exactly x equals 3. So the domain we can write as x not equal to 3, or in interval notation, we write it this way. And we introduce this new notation. This is the symbol for union. It means that the domain is everything from -infinity to 3, given by this left side piece, and everything from 3 to infinity. And the parentheses next to the 3 in this interval and next to the 3 in this interval indicate that 3 itself is not included in the domain. Our second red flag is that we can't take the root of a negative number. So for instance, if we have this function, k of x equals square root of x minus 1, because we have this root here, the value underneath the root cannot be negative. It can be 0 and it can be positive, but it can't be negative, which means that x minus 1 has to be greater than or equal to 0. We take the value under the root and we set it greater than or equal to 0. Then we can solve this inequality by adding 1 to both sides to get x greater than or equal to positive 1. So for the function k, the domain is all x greater than or equal to 1. If we want to write that in interval notation, because x can be equal to 1, we write the 1 here with a bracket around the 1, indicating that 1 is included in the domain. And we say the domain extends all the way to infinity. So the domain is 1 to infinity with 1 included. Keep in mind that for this red flag, for this rule, what we're really saying is that we can't take the even root of a negative number. So this rule holds for a square root like this one. It also holds for a fourth root or a sixth root, any even root. But if we have an odd root, like a cube root, then the radicand, the value inside the root, can potentially be negative. So our rule is really that we can't take the even root of a negative number. And our third rule, our third red flag, is that the argument of a logarithm has to be strictly positive. So for instance, if we're taking log of x minus 2, because x minus 2 is the argument of this logarithm, x minus 2 has to be positive. It has to be greater than 0. It can't be negative and it can't be equal to 0. So we set that argument greater than 0. We solve that inequality for x by adding 2 to both sides. And in this expression, this function, x has to be greater than 2. Remember, we're looking for values that can't be in the domain based on these three rules. We're not looking for every value that can be in the domain. So if we don't see any of these red flags in our function, we can conclude that the domain is all real numbers. For example, any polynomial function like this one, x squared minus 2x plus 1, there's no denominator, so we don't have to worry about dividing by 0. There are no roots, so we don't have to worry about taking the even root of a negative number. And there are no logarithms. So because none of these three red flags are things we would need to consider for this polynomial, that means right away, we don't have to test every value on the real number line. We can conclude that this function's domain is all real numbers, or negative infinity to positive infinity in interval notation. So that's all well and good. We know the flashlight technique for finding domain and range from a graph, and we know these three red flags, these three rules we have to look out for when we have the actual equation of the function instead of the graph. But what do we do when things change? For instance, when we have a piecewise defined function, does that change our domain and range rules or techniques at all? Well, really, we're still just following the same process. Whether we have this function or its graph, this is a sketch of the graph of this piecewise function, we're still using the same techniques. First of all, when we have a piecewise function, we can get the domain directly from the function itself. This tells us that f is defined by this piece whenever x is less than -1, and this piece defines the function whenever x is greater than or equal to -1, which means this function is defined for the entire real number line for all real numbers, which we can indicate with this symbol here for all real numbers, or as we've seen before in interval notation, from negative infinity to positive infinity. So we get the domain right away from the equation of the function. We could also see if we looked at the graph that this sort of parabolic shape would extend infinitely to the right, and this line on the left side of the graph would extend infinitely to the left, and so we would in fact get a shadow from this graph that is the entire real number line, the entire x-axis. So for piecewise functions, we can easily get the domain from the function itself or from the graph. What about the range? Well, from the graph here, we can see that this sort of parabolic shape would cast a shadow along the y-axis from +2 at the top end down to negative infinity. And this linear part of the graph on the left-hand side here, if we shine a flashlight from the left against this line, it would add this tiny little piece of shadow between y equals 2 and y equals 3. But no shadow would ever be cast above y equals 3, so the range is going to be everything y less than 3, not including 3 itself, because of the empty hole here in the linear part of the graph. This part of the graph is the x plus 4 part, and it's defined for x less than -1. So this value right at x equals -1 is not included in the function, which is why we say y less than 3 instead of y less than or equal to 3. And of course, if we want to write that in interval notation, that's everything from negative infinity all the way down here at the bottom to +3, not including +3, which is why we have the parenthesis here instead of a bracket. So we know nothing changes with piecewise functions, but now things are starting to get tricky because we're going to have to combine multiple red flag rules about finding the domain, and that can present us with extra challenges. So take, for instance, this function, g of x equals root x plus 2 divided by x minus 5. Well, what do we know about our red flags? The first thing we know is that the value inside of a square root can't be negative, which means x plus 2 has to be greater than or equal to 0. It's got to be non-negative. We also know from one of our other red flag rules that the denominator can never equal 0, which means that for g of x, it also has to be true that x minus 5 is not 0. So both of these things must be true at the same time. We have two inequalities that we have to deal with. So let's deal with this one on the left first. If we subtract 2 from both sides of the inequality, we get x greater than or equal to negative 2. And over here on the right, if we add 5 to both sides of the equation, we get x not equal to positive 5. So it has to be the case that x is both greater than or equal to negative 2 and not equal to 5. So let's look at this a couple of ways. If we sketch a number line, the real number line here, with 0 in the middle, we see negative 2 over here on the left, this is positive 5. We could sketch this domain this way. We know that the value negative 2 itself is included in the domain because we have x greater than or equal to negative 2. So we sketch a solid circle here at negative 2, and we know x is greater than negative 2, so we extend a sketch of the domain out to the right on the real number line. That line goes forever, except that we have to have this hole here at x equals 5 because x cannot be equal to 5. So this is a sketch of the domain, but in interval notation, we could write it this way. We could say x extends from negative 2 on the left, including at x equals negative 2 itself, and it extends all the way until we get to 5, but without 5 being included. And then it also includes all values to the right of 5, not including 5 itself, all the way to infinity. So in interval notation, this is the domain of g, but of course we had to account for two of our red flags, one about taking the root of negative numbers and one about the denominator being 0. So we've seen these rules combined. Let's look at a couple more tricks before we do a challenge. It can sometimes be helpful to solve the equation of a function for x in terms of y. So let's say we're given y equals root x minus 1. Well, we could solve this for x by first squaring both sides. So we get y squared on the left, squaring the right side takes away the square root. And then if we add 1 to both sides, we get x equals y squared plus 1. We've solved this for x in terms of y. Now here's why this can be helpful. We know from the original function that this root has to be non-negative. We can't take the square root of a negative number, so x minus 1 has to be non-negative, which means when we take the square root of that non-negative value, we're going to get a non-negative value for square root x minus 1. We can get 0, and we can get a positive value, but we can't get a negative value. What this equation tells us then, the equation of the function, is that y has to be non-negative, and because y represents the range, we know right away that the range is 0 to infinity with 0 included. But then, having solved the function's equation for x, we see that we have y equal to this expression in the original equation, but then we have y here. We know that y has to be non-negative, and when we square a non-negative value, we're again going to get a non-negative value. And when we add 1 to that non-negative value, we'll still have a non-negative value. So this whole thing, y squared plus 1, also must be non-negative. Because y can only be 0 up to positive infinity, y squared plus 1 also has to be 0 to positive infinity, and therefore the domain represented by x has to be 0 to positive infinity. So that was a quick way to find the domain by solving for x in terms of y. That can sometimes be helpful. Sometimes we'll also have more complicated functions like this one, where we have the log of a polynomial argument. Here's why this gets a little tricky. We already know that the argument of the log function has to be positive. It has to be strictly greater than 0. So we set x squared minus 5x plus 6 greater than 0. But now, in order to solve this inequality, we have to actually factor the left side of the inequality. X squared minus 5x plus 6 factors as quantity x minus 3 times quantity x minus 2. And now things get a little tougher because we have to realize that we have two values multiplied together. We have x minus 3 and x minus 2. Those two things are multiplied together. When we have the product of two values, how do we get a product that is positive? Well, if one of those values is negative and the other is positive, when we multiply them together, we get a negative value. A negative times a positive is a negative. The only way to get a positive value from the product of two numbers is for both of those numbers to be negative or both of them to be positive. So we have to say that either x minus 3 is less than 0 and x minus 2 is less than 0. They're both negative. Or they're both positive. X minus 3 is positive and x minus 2 is positive. So the domain actually has to satisfy this entire statement. What we need to do is simplify each inequality. This x minus 3 less than 0, when we add 3 to both sides, becomes x less than 3. And the x minus 2 less than 0 when we add 2 to both sides becomes x less than 2. When we simplify the other inequalities as well and keep the whole statement, we get this statement for the domain. But now we want to look at each piece individually. So if it has to be the case that x is less than 3 and that x is less than 2, if both of those things have to be true at the same time, the only way they can both be true at the same time is if x is less than 2. Because x could be less than 3, let's say 2.99, which would satisfy this inequality, but not this one. 2.99 is not less than 2. The only values that satisfy these two statements are the values x less than 2. And then same thing here, it has to be the case that both x is greater than 3 and greater than 2 at the same time. And the only way for that to be true is for x to be greater than 3, which means these two inequalities are the ones that govern the domain. And therefore, we have to say that the values of x in the domain satisfy x less than 2 or x greater than 3. Now, if we want to visualize that, we can build ourselves a real number line. We have 0 here, and then 2 and 3. We know x has to be less than 2, which we can sketch this way with an open circle at 2 because 2 itself is not included. Or we know x has to be greater than 3, which we can represent as this piece, again with an open circle at x equals 3 itself. Or we could write that in interval notation as negative infinity to 2 with 2 not included, and 3 to infinity with 3 not included. So any values in this set are going to be values included in the domain. So one more challenge to wrap up, where again we have to consider multiple red flags of our 3 red flag rules. We know that 9 minus x squared has to be greater than or equal to 0 because the value under a root has to be non-negative. But we also know that the denominator of a fraction can't be equal to 0. So the square root of 9 minus x squared can't be 0. Both of these rules are affecting the denominator. So how do we handle this? Well, we can think about it logically. If this whole root here, root 9 minus x squared, can't be 0, then if over here, if 9 minus x squared were equal to 0, that would put a 0 under this root. We'd be taking the square root of 0, and that would equal 0, which means we can't have 9 minus x squared greater than or equal to 0. We just have to have 9 minus x squared greater than 0. That's the only way to also keep this equation true. And if 9 minus x squared is greater than 0, that's going to guarantee that the square root of 9 minus x squared is not 0, because we're going to have a positive value out of this rule. And when we take the square root of a positive value, we're going to get a positive value, which of course will not be equal to 0. So the only rule we really care about is 9 minus x squared greater than 0. That's the singular rule that's going to define the domain of G. So that's all we need to worry about. We solve this inequality for x squared by adding x squared to both sides, and then we can just flip this around so it's a little easier to read and read it as x squared less than 9. But now, how do we deal with an x squared in an inequality like this? Well, let's think about it. If we were to take the square root of both sides of the inequality, we would get x less than positive or negative 3. So we know positive and negative 3 are going to be important values to pay attention to. So we could sketch a real number line like this. We'll put 0 in the middle, negative 3 and positive 3. Let's think about values that are to the left of negative 3. For example, negative 4. If we try to plug in negative 4, we get negative 4 quantity squared is a positive 16. 16 is not less than 9, which means values to the left of negative 3 are not going to be included in the domain. Same thing to the right of positive 3. If we take positive 4 and plug it in, we get 4 squared or 16. 16 less than 9, that's not true. So values to the right of 3 are not included. But if we test anything in between negative 3 and 3, we'll get an inequality that's true. If we test 0, we get 0 less than 9. That works. If we test negative 1, we get 1 less than 9. That works. If we test positive 1, we get 1 less than 9. That also works. So the domain is going to be from negative 3 to 3, not including negative 3 and 3 itself, because think about it. If we test exactly x equals negative 3, we get negative 3 quantity squared is positive 9, and the inequality becomes 9 less than 9, which of course isn't true. So negative 3 itself can't be included in the domain, and for the same reason, neither can positive 3. Whenever you're looking at a domain, it's critical to think about these endpoints and always make sure you pay special attention to them, test them in this inequality, because that's where it's easiest to get messed up, to include negative 3 or include positive 3 in this domain when they shouldn't be. So the domain is negative 3 to positive 3, not including either one. And then what's the range? Well, remember, we already said that 9 minus x squared has to be positive. So this value underneath the root has to be positive, which means we're taking the square root of a positive number. That's always going to give us a positive number. So no matter what we plug in for x, we're going to get 1 divided by a positive number. That means the result over here on the right-hand side will always be positive. So g of x, or y, will always be equal to a positive number. It's impossible for us to get 0 or negative anything on this right side. So the range is everything from 0 to positive infinity, not including 0 itself. So as a recap, if we have the graph and only the graph, use the flashlight technique. Think about shining a flashlight from above, below, to the left, and to the right of the graph. And the domain is given by the shadow along the x-axis. The range is given by the shadow along the y-axis. But if we have the equation of the function, we want to think about the 3 red flag rules. Remember, we never want to try to look for every value that the function can take in. We only want to look at the values that it can't take in. Denominators cannot be 0. What's inside an even root cannot be negative. It has to be non-negative. So that expression inside the root has to be greater than or equal to 0. And the inside of a log function, the argument of the log function, has to be strictly positive. It can't be equal to 0. It can't be negative. So the argument of the log has to be positive. And if a function doesn't have any values that violate one of these 3 red flags, if there are no red flags, then that automatically means that the domain is all real numbers, which we write as this way, or negative infinity to positive infinity. Remember that if you want more help with domain and range, don't forget to check out my algebra courses down below and give this video a like if it helped.